today we're going to look at 10 of the most mysterious unsolved questions surrounding our universe.
Another strange thing we can't figure out surrounds the Higgs boson. Discovered back in 2012, the Higgs boson made headlines when it was finally observed at the Large Hadron Collider. Finally, scientists had found this God particle. The particle makes up the Higgs field, which gives mass and force of all the other particles in our universe. Without it, atoms would disintegrate, and the universe as we know it, wouldn't exist. It was like finding a missing link. The Higgs boson had existed in theory for years, but now physicists had physical evidence to prove it.
But there was one problem. If the Higgs boson controls the mass and force of everything, then it should also be applied to gravity. But the boson is super lightweight. Now, the mass scales that gravity acts upon, like you and me and the planets and your friend tripping and falling over a rock, right, are trillions of times larger. It seems that there are some irreconcilable phenomena going on here between the micro and the macro levels. Scientists call this problem the hierarchy problem.
It's weird that the Higgs boson is so lightweight. Super heavy gravitational states should mix together in a quantum mechanical way with the boson and affect its mass. But they don't. It's like all the really heavy stuff has just magically cancelled out and left a very lightweight boson with a tiny yet constant mass behind. This is suspicious to many scientists who've compared the problem to a pencil that seems to stand straight up on its tip without ever falling over. It seems like such a fine-tuned improbability that it's led many to wonder whether there is really a natural order to anything, or whether our universe is really just a, freak accident, unnatural even.
Time plays a huge part in our everyday lives. I mean, without time, life would be, chaos, right? But physicists are still trying to understand exactly what time is. Now, some theories propose that time might not even exist as an independent and fundamental concept in the same way we think we perceive it.
In our everyday lives, we experience time as something that constantly flows forward from the past to the present and into the future. But in physics, there are theories that suggest that time isn't a separate entity, but instead part of a larger framework that includes space and other fundamental forces. One such theory is called quantum loop gravity. It's a theoretical framework that tries to combine the principles of quantum mechanics and general relativity, a whole separate mystery that we'll get into shortly. In quantum loop theory, the fabric of space itself is made up of tiny loops or threads, and these loops interact and give rise to the properties we observe, like matter and the forces of nature.
In loop quantum gravity, time isn't fundamental. Instead, it emerges as a kind of illusion or approximate concept on large scales. It's like how we might say that the hats and glasses exist, but when we study the fundamental particles and forces of physics, we don't directly consider hats and glasses.
The idea is that time, as we perceive it, might be an emergent property that arises from the interactions of the underlying quantum structure of the universe. You've landed in the solar system GW Orionis, one of the rare systems with 3 stars. Astronomers believe that about half of the known solar systems in the universe actually have 2 stars, but a 3-star system, it's pretty rare. In GW Orionis, 2 of the stars are locked in a tight rotation around each other, and the third is just a little bit further off, spinning wildly around the other 2.
You've landed on one of the rarest planets in the universe. The planet orbiting the 3 suns is the first of its kind ever discovered by astronomers, something called a circumtriple planet, and it's huge. It's bigger than Jupiter, but unfortunately it's a gas giant that's impossible to live on, and you're pretty upset that you've ended up all the way out here. Weren't you just sort of stuck in traffic on the LA freeway a second ago?
Strange matter is a hypothetical form of matter that's composed of strange quarks, a type of elementary particle. Now, quarks are the building blocks of protons and neutrons that make up the atomic nuclei. Strange quarks are considered strange because they're heavier and more unstable compared to the up and down quarks found in ordinary matter. They're proposed to form under the super-duper pressurized innards of neutron stars. The core of a neutron star is so dense that the atoms become pressurized to the point where their protons and neutrons burst apart into quarks. According to some theories, if strange matter comes into contact with ordinary matter, it could convert it into strange matter through a process called strangification. The idea is that strange matter is more stable than ordinary matter, and it has a lower energy state. So if strange matter were to come into contact with an atomic nucleus, well, it could potentially engulf it and convert it into a strangelet.
Is our universe infinite or finite? Scientists have a pretty good idea that it's at least expanding. So does that mean that it's finite? How can something infinite be expanding, right? And if it's finite, what is the universe expanding into? And if it's not expanding into anything and simply stretching, as a lot of physicists suggest, then what does that actually mean? These are all questions that scientists and philosophers have been grappling with in one way or another for millennia.
First, let's look at the arguments for a finite universe. Now, one possibility is that the universe is finite and closed, meaning that it has a finite volume and is shaping something like a hypersphere or a torus. In a closed universe, if you were to travel in a straight line for a long enough distance, you'd eventually end up back to where you started. Big-name physicists like Stephen Hawking and Roger Penrose have proposed models of a closed, finite universe. Another theory suggests that the universe is finite and will eventually collapse under its own gravitational pull in a scenario called the Big Crunch. Now, according to this idea, the expansion of the universe will eventually reverse, leading to a contraction that ends in a high-density state similar to the singularity-type Big Bang that started the ball rolling in the first place. Or, well, not rolling really, but expanding. Then we've got the theories of the infinite. An open universe is a theory in which the universe is infinite and has no boundaries. It expands forever without collapsing. In this scenario, the expansion of the universe will continue on and on and on. Scientists like Alan Guth and Andre Linde are two big names in something called inflationary cosmology, which suggests that our universe may be part of a vast, infinite multiverse. The Fermi paradox is a question that arises from the apparent contradiction between the high probability of the existence of other life-form civilizations and the lack of evidence or contact with them. It's named after the physicist Enrico Fermi, who famously asked, "Where the heck is everybody?"
The paradox stems from the vast number of potentially habitable planets in our galaxy and the universe, coupled with the immense age of the universe. Now, a guy named Frank Drake, no, not that Drake, this one. Yeah, there he is. So, Frank Drake scribbled down an equation called the Drake equation, which is a sort of type of probabilistic framework that suggests that there should be a whole bunch of advanced civilizations capable of interstellar communication.
The equation takes into account factors like star formation, percentages of planets in habitable zones, and probabilities for life developing to a point where it can communicate vast distances. The Sun, despite being the star at the center of our solar system, is still
pretty mysterious thing to us. While we've got a good understanding of its general behaviour, there are intricacies in its physics that have left a lot of scientists just scratching their heads. This lack of complete knowledge about the sun's inner workings affects what we know about solar flares, sunbursts that can, at any time, destroy life as we know it on our pale blue dot.
Solar flares are powerful eruptions of energy from the sun's surface, releasing intense bursts of radiation and charged particles into space. These events can impact our technology, communication systems, and even pose a potential risk to our power grids. However, predicting the timing and the magnitude of solar flares accurately is challenging because of everything we don't know about the sun and its complex dynamics. In a plasma, magnetic field lines can become twisted or tangled due to various factors, including the movement of the plasma itself or the presence of different magnetic fields. When these tangled magnetic field lines interact, magnetic reconnection happens.
During magnetic reconnection, the opposing magnetic field lines break and then form new connections with each other. This rearrangement releases a tremendous amount of energy, which can cause explosive events such as solar flares on the sun or geomagnetic storms in Earth's magnetosphere. Forget about if there's life on Mars. Is there life on Titan? And if there is, it could be pretty wild, Now, Titan, Saturn's largest moon, has fascinated scientists for a long time because of the presence of hydrocarbon lakes and seas on its surface. One of the most intriguing mysteries surrounding Titan is the possibility of liquid oceans beneath its icy crust and the potential for life to exist within them.
The potential for life on Titan centres around the idea of weird life. Unlike the life forms we're familiar with on Earth, which rely on liquid water as a solvent, potential life on Titan could utilise liquid hydrocarbons like methane or ethane as a basis for its biochemistry.
If we're ever going to answer the Fermi paradox, we'd better get out there and start looking. And in fact, looking we are. In 2010, only around 500 exoplanets had been detected anywhere in our universe. As of 2023, there have been nearly 10,000. We're making huge strides in finding potentially habitable planets outside of our solar system, planets that sit right in what's called the Goldilocks zone. That's where they're not too far and not too close to their respective stars.
Just recently, the newly launched James Webb Telescope gave us the first definitive glimpse at an atmosphere of an exoplanet. It honed in on a planet dubbed WASP 39b, that's some 700 light years away. The planet's been described as a hot Saturn. Not that it's better looking than our planetary neighbour, no, it's just, literally hotter. Webb was able to detect things like the chemistry in its clouds, the fact that they don't envelop the entire planet, and the fact that it has sulfur dioxide in its atmosphere.
Now, as we know, there's a supermassive black hole at the centre of every galaxy in the universe, but the thing is, we don't really know how they're formed. Supermassive black holes are incredibly massive objects, hence the name, with millions or even billions of times the mass of our Sun, residing at the centres of galaxies. Now, a few theories and mechanisms have been proposed to explain their formation, but none of them have been definitely proven. Here's a few of the leading theories.
Accretion and mergers. Another possibility is that supermassives grow over time through the accretion of mass and the merging of smaller black holes. Gas and dust falling into the centre of a galaxy can provide material for a black hole to grow. It basically just gobbles up stardust and gets nice and fat. There are also galactic mergers where two or more galaxies smash spectacularly into each other, which could possibly bring together multiple black holes that eventually merge to form a supermassive black hole. primordial black holes. Supermassive black holes could also have formed during the universe's infancy, a phenomenon called primordial black hole creation. These could have emerged from fluctuations in the density of the early universe. These black holes would have started with a significant mass, and over time they could have grown into supermassive black holes through the accretion or mergers that we just mentioned. But there are two significant questions swirling around like our Milky Way galaxy about just how the hell was all of this possible? Which brings us to, what other mysteries are out there? Let us know in the comments, and don't forget to like and subscribe for more universal Factnominal content.